2B classification of matter. 2.7 a classification model. Classification is one of the first things that humans did in obedience to the creation mandate, Genesis 2:19-20. As Adam named the animals in the Garden of Eden, he likely separated them into their kinds based on their appearance. See Figure 2-10. Classification helps us understand our world. We organize what we know into familiar patterns in a way that helps us remember and make sense of what we learn. In Section 2A, you classified all the matter you could see in the room around you. Beyond simply grouping the substances into states of matter solids, liquids, and gases, the task seems almost hopeless. There are millions of substances, and many materials, like concrete or granite, are made of more than a single substance. Where do you begin? We need a classification model to help us categorize matter. As with any model, the system won't be perfect, but it will be workable for the purposes of this course. Figure 211 illustrates the model we will use for the classification of matter. 2.8 Pure Substances. We classify substances by the kinds of particles they are made of and how they are combined. The first category we will use includes all the pure substances. Those materials made of only one kind of substance. An element is the simplest kind of pure substance and is made of only one kind of atom. Elements can exist as single atoms, as molecules of one kind of atom, or as masses of uncountable atoms of the same kind. Compounds are the other category of pure substances. A compound contains more than one kind of atom chemically bonded together. The atoms of compounds may link up in molecules or in great masses of ions arranged in a repeating geometric pattern called a lattice. But for a given compound, they always combine in the same proportions. Chemists sometimes subdivide compounds into two major groups, organic and inorganic compounds. Organic compounds always contain the element carbon, and many of these are found in or are produced by living things. Other elements, such as hydrogen, oxygen, nitrogen, and phosphorus, can be present in organic compounds. There are over 50 million known organic compounds, and most new compounds developed each year are organic compounds. The other compounds, including a few that do contain carbon, like carbon dioxide, as well as all that don't, are inorganic compounds. 2.9 Mixtures. Mixing two or more substances together forms, you guessed it, a mixture. These substances may be elements, compounds, or even other mixtures. The substances in a mixture are not chemically combined. This is the main difference between a compound and a mixture. The proportions of the substances that make up mixtures can also vary widely. The parts can be mixed in equal amounts, or only a few molecules of one substance could be mixed into another substance that forms most of the mixture. Mixtures are very common in our world. Rock, soil, air, blood, and seawater are just a few examples of mixtures. We can sort mixtures into two main groups based on how the particles of their substances mix. In homogeneous mixtures, the particles of the different substances are roughly the same size and evenly mix. We say that the mixture of substances is uniform by sight and at the particle level. If these mixtures are gases or liquids, we can also call them solutions. The air that you breathe, tap water, gasoline, and many metal alloys, such as those used in gold jewelry, are common examples of homogeneous mixtures. Mixtures made of particles that differ greatly in size are heterogeneous mixtures. These mixtures are not uniform. You can often see the different substances with the unaided eye, or under a low-power microscope. A familiar example of a heterogeneous mixture is the rock called granite. It usually contains three visible types of minerals: dark biotite, light pinkish feldspar, and white or clear quartz. Scientists call visually distinct parts of a mixture phases. Thus, there are three mineral phases in granite. See Figure 2.15. Other examples of heterogeneous mixtures include whole blood, soil, whole milk, home-cooked stew, and gravel. 2.10 States of matter. We normally find matter on Earth in one of three physical forms, or states: solid, liquid, or gas. Because many materials can exist together in more than one physical state, scientists refer to the different states as phases. just as if they were a heterogeneous mixture. The glass of water in Figure 2.16 contains three phases of water. Ice is the solid phase. The water itself is the normal liquid phase. The bubbles in the water contain water vapor, the gaseous phase. How can one material exist in different physical states? In our kinetic molecular model of matter, extremely tiny particles are in constant random motion. Long ago, scientists found that a substance's physical state depends on the strength of the attraction between its particles and how fast they're moving. Atoms and molecules that are similar have some attraction for each other. The strength of attraction is related to the distance between particles. Close together, the particles strongly attract. The attraction drops off rapidly as the particles draw apart. At a distance, the particles have no attraction. The speed of the particles' random vibrations and the temperature of the substance are also related. The slower the particles move, the lower the temperature. The faster they move, the higher the temperature. You will learn why this is so later in the course. Standard conditions. The state of a substance depends on the kind of substance and the conditions surrounding it. The state of matter also relates in some way to temperature. Many properties of substances can change as temperature, atmospheric pressure, and other conditions change. To accurately classify and compare different substances, scientists need to compare their properties when measured under identical conditions. For example, an oceanographer who wants to compare the density of a sample of seawater with that of pure water would need to make sure that they were the same temperature, since temperature affects density. Otherwise, the comparison would be meaningless. Most measurable properties of many substances have been recorded in reference lists used by scientists and educators. Researchers, mostly materials engineers and mineralogists, likely measured these properties at a standard temperature and pressure, STP, when Nick Essery. These conditions are typically 0 C and average atmospheric pressure at sea level, e.g., 1013 millibars. When discussing the properties of the different states of matter and the properties of matter in general later in this chapter, we will assume the substances are at a standard temperature or pressure. Solids. Solid materials make up most of the Earth's matter and most of the physical objects familiar to you. Your pencil, your desk, a rubber band, the fabric in your clothing, a computer, and even the room you are in are solids. What makes a solid different from the other states of matter? Solid objects don't easily change shape, they don't flow, and their volume is basically constant. Most are hard and rigid. The range of particle random motion in solids is very limited. This is what determines its main properties. Particles of a solid are close together and occupy definite positions. They randomly vibrate in those locations, continuously rattling against their neighboring particles, but otherwise they don't move from their fixed locations. This explains why the solid state of a substance is usually the densest. The particles are normally much closer together in a solid than in its liquid or gaseous states. The vibrations of the particles of a solid substance also have the slowest motion of any of the three states of that substance. It is cooler than when in its liquid or gaseous states. The cozy arrangement of particles in a solid explains another important property of most solids' low compressibility. Since particles are already practically touching, it is difficult to squeeze them closer. Atoms strongly repel other atoms if they get too close together. The arrangement of particles in a solid varies, depending on its chemical composition and the way the solid formed. The particles in a crystalline solid are arranged in geometric patterns that can repeat without limit. Solids of this kind often form crystals. Atoms and molecules in solids can also be randomly arranged. These are amorphous solids. The particle structure of real solids may lie anywhere between these extremes, or can be a combination of them. Material scientists have grouped solids into at least 11 types, though some may overlap with others. Most metals are clearly crystalline, with closely packed repeating patterns of atoms. Crystalline earth minerals often produce beautiful crystals. Most glasses are common examples of amorphous solids. In between crystalline and amorphous structures are materials like ceramics and ceramic glasses. Advanced ceramics are composed of tiny crystalline particles that are compressed together under high temperature and pressure, producing a polycrystalline structure. Pure organic solids like wax are generally amorphous. However, some natural organic solids have definite structures, like wood or bone, which consist of organic fibers embedded in amorphous or crystalline compounds. Artificial and natural organic compounds can form useful solids called polymers, which are long chains or nets of identical, linked molecules. Latex, silk, plastics, and synthetic fabrics are all made from polymers. Advanced materials that human creativity has developed within the last century include composite solids like carbon fiber resin, which is both strong and somewhat flexible. The computer chips that are the hearts and brains of all digital electronics are composed of artificial crystalline semiconductor compounds. We continue to develop even stranger but very useful solids, including aerogels and aerographites, as we exercise dominion, shaping the resources of the world in ways that best serve our needs. Liquids. A liquid has two main physical properties. It has a definite volume like a solid, but it flows. It isn't rigid. This is why scientists call liquids fluids. On Earth, a liquid takes on the shape of its container and fills the container from the bottom up. Because of this, a liquid normally has a free surface if it doesn't completely fill its container. An undisturbed free surface lies flat, but waves can move through it. In a microgravity environment, like that inside the International Space Station, a liquid naturally forms a wobbly sphere. Its free surface is the outside of the sphere. The particles in a liquid are much freer to move around than those in a solid because they aren't trapped in fixed positions by strong attractions to their neighbors. They vibrate and freely spin. But the still strong attraction between particles keeps them close together, so liquids have low compressibility like solids. The particles in a liquid move easily among each other, colliding almost continuously with other particles. The mobility of particles in a liquid allows them to flow easily from one place to another. This fluid behavior allows liquids to pour, to flow through pipes, and to form rivers and streams. The ability to flow varies from one liquid to another. For example, rubbing alcohol pours easily and seems to flow everywhere when it spills. On the other hand, corn syrup is very thick and takes a long time to pour out of a bottle. A liquid's resistance to flow is called viscosity. A liquid's viscosity depends on the strength of attraction between the liquid's particles, how tangled up the particles become due to their shape, and how rapidly the particles randomly move, again related to the liquid's temperature. Liquids generally become less viscous as their temperature increases and more viscous as they get colder. Viscosity is especially important in liquids called lubricants. These substances reduce friction by forming a thin film of liquid between smooth sliding surfaces, which improves slipping and reduces wear. Gases. The molecules in a gas are far apart and move at high speeds compared to the particles in liquids or solids. They randomly vibrate just like the particles in solids and spin as in liquids. But particles in the gaseous state also move very fast in straight lines until they collide with something. A typical particle in a gas at room temperature moves at about 490 meters per second, or about 1.5 times the speed of sound. Gas molecules near the surface of the Earth collide with each other billions of times a second, and act like tiny billiard balls bouncing off one another when they do collide. A quantity of gas doesn't have a definite shape, like a solid. Neither does it have a definite volume, like a liquid. When a gas flows into an empty sealed container, its molecules will quickly move to every part of the container. Very shortly, the gas uniformly fills the available volume. If a sealed container has one kind of gas in it, and another kind of gas enters the container, the second gas may take a long time to diffuse into the original gas, especially if their densities are very different. They will first separate into layers. Gases, like liquids, can flow from one place to another. You can pour pure carbon dioxide into a beaker because it is denser than air. Cold, dense. Nighttime air can flow down a mountain into a valley, displacing a blanket of warmer air. compressed air can flow through pipes. Thus, just like liquids, gases are fluids. Some containers, such as the space inside a bicycle tire pump, can change shape and volume. If you push in on the pump handle while holding your thumb over the nozzle, the air in the pump is squeezed into a much smaller volume. You can see that gases are highly compressible. Molecules of a gas in a sealed container collide not only with one another, but also with the walls of the container. Imagine how the gas molecules bombard the walls of the container. Billions of them hit each square centimeter every second. You would never notice the force of a single molecule, but the impacts of billions of molecules can produce a significant push spread out over the area of the container's walls. The force a gas exerts on an area is gas pressure. Gas pressure exists even if a gas isn't trapped in a container. The air molecules in the atmosphere exert a pressure that we can measure with special instruments.